Assalamualaikum. How are you, Shabir?
I'm good.
Hope you are doing well and everything is fine over there. Hope you are fine. Is my voice is clear?
Yeah, I'm good.
My voice
Yeah,
is okay. So, are you ready for today's lecture number 14? Have you revised what we did in previous lecture? Have you go through those
yeah,
lectures? Okay. Any question regarding previous lectures?
yeah.
Any
Nah,
Okay. Everything okay?
yeah,
Okay. So let's start our today's lecture. So let me share my screen with you. So my screen is sharing with you, right?
yeah,
Okay, so today is our lecture number 14, and in this lecture, basically, we will discuss about the motion of satellites, and we will discuss about orbits, how satellite moves and how they orbits around the Earth. You know that many planets are revolving around a massive planet, which is so called as Sun. Every planet is revolving around the sun, and there are some other satellites also that are revolving around our Earth too, like Moon. Moon is also one of the satellite that is revolving around our Earth. So we see some difference between types of satellites, and we see the difference how they orbit around different objects. So this is all about our today's lecture. Our learning objectives are we will understand what satellites and how and what are their motions, how they will move under the action of gravity. Then we will move on towards types of satellites. There are basically two types of satellite. The first one is so called as the natural satellite, and the second one is called as the artificial satellite. Then we will discuss what is geostationary and lower Earth orbit. Okay. Then we will move on towards, we will see the concept of centripetal force. We already did this topic. You already know what is centripetal force. Can you tell me a little bit about centripetal force?
um, I don't know. Can't remember.
Okay, basically, centripetal force is a force in which your body is revolving around a body. Okay, if a body is moving in a circle and that body is moving around some specific point or body, this type of motion is called as centripetal motion, and the force related to that is centripetal force. Now it's okay.
Yeah,
Okay, then we will apply Newton's laws of motion to these centripetal force or circular orbital motions of the satellite. You know how many laws of Newton's are there? There are three laws of Newton.
yeah,
We will apply those Newton's laws in this topic. And at last, we will drive a relationship between orbital speed equation. We will drive an equation for that also. So let's start with the definition of satellite. What is satellite? How can we define a satellite? So basically, a satellite is an object that revolves around a larger body in space, okay, due to the influence of gravity. If a body is moving around a larger body, and the motion of that body must be due to the influence of gravity. If that's so we can say that object is so called as a satellite. Okay, the object that is moving around a massive body under the action influence of gravity, that object is so called as the satellite. All right.
yeah,
Hmm. Basically, it maintains its orbit by balancing two factors. What those two factors are? Its forward motion as well as the pull of the gravity from the planets or star. You can see here, this is our larger planet. You can say this is our planet Earth, which is a massive body, and there are some two different satellites are revolving around them. The one is the moon, and the other is the some satellite. Moon is so called as the natural satellite. Why this is called as the natural satellite? Do you know? Why
Yeah,
moon is so
because
called as the natural satellite? Because it is made by, it is man-made or not?
it's not man-made. It was
Uh,
made by itself.
yes, itself. So if this is not man-made, so that's why definitely this is natural. So that's why everything that is revolving around a body which is massive. So yes, our moon is also revolving around our Earth. So moon is also a satellite, and this is a natural satellite, whereas this is a satellite which is man-made, right?
Yeah,
So everything that is revolving around an Earth or every massive body and which is man-made, this type of satellite is called as the artificial satellite. Okay, so here you can see the definitions of natural satellite and artificial satellite. There are celestial bodies formed by the nature. The bodies which are made by nature, like moon and some other stars, this is all made by nature. So this type of satellites are called as the natural satellites. Like the moon is revolving around the earth. This is one of the natural satellite. Next is the artificial satellite. Those satellites which I told you, man-made machines, which will self-launch into the space. This type of satellites are called as the artificial satellites. Okay, examples are GPS, global positioning system, you know, communication satellites, weather satellites. Okay, so these are the examples of artificial satellites which are man-made and launched by humans into the space. And those bodies are revolving around the Earth. That's why they are called as the artificial satellites. All right.
yeah,
Next, satellites do not need propulsion. Propulsion means they do not need external force when they stay in orbit once correctly launched. Once you launch the satellite, initially you must need propulsion. You must need an external force to launch the satellite into the space. But when you once launch the satellite into the space, now your satellite is freely to move under the action of gravity. They do not need more propulsion, more external force to revolve around the earth. Okay, this is all due to with the help of gravity. Gravity helps things to move in a circle. Okay.
yeah,
Hmm. So once you launch the satellites, then they do not need any more propulsion. Okay, they automatically move in a curved path. But how? Because of the gravitational pull, okay, of the earth. The next thing is, the next concept of a satellite is that this is very essential in physics. Some applications are astronomy, telecommunication, okay, weather forecasting, navigation system, and many space exploration systems. We are using these satellite concept. Any question?
no,
Okay. So here you can see the next thing is orbits and forces. Now, how your satellites orbits? What does this orbit means? Orbit means revolving, okay? And forces mean what type of forces related to when your object is revolving. Definitely, the one and only force which is relevant to this topic is the gravitational force, okay?
yeah,
Hmm. So satellites stay in orbit due to the centripetal force provided by the gravity. I already mentioned you before, once you launch the satellite into the space, now they do not need any more propulsion. Now they move. in a circular path. And circular path, this type of force is called as the
uh, centripetal
yes,
force.
centripetal force. So if an object is now moving in a circular path, so you can say the force related to that is the centripetal force, and your object is now moving under the action of gravity. That's why gravity is very, very essential. If there is no gravity, so definitely your object would not revolve. They would move straight away. Okay. No engine needed once in stable orbit. Same thing which I mentioned. Okay, the important thing is that what is the speed of your satellite? The higher
Yeah,
the orbit you go, the slower the speed will be. Okay, higher orbit means basically you are moving away from the Earth. Let's suppose Earth and Moon. Okay, so if Moon is revolving very, very away from the Earth, so definitely their speed will slow. And if an object is revolving very close to the Earth, so their speed would be high. So orbital speed is an inverse relation with the speed. Okay, higher orbit basically is the inverse
yeah,
relationship with the speed. The more the speed, the less will be the orbit. Okay, if the orbit is higher, means the distance between two bodies is higher, means so you can say the speed will be slow. Any question?
yeah.
Okay. Now let's move on towards an important thing, the derivation of orbital speed. We already discussed orbital speed, but how can you derive the mathematical relationship of orbital speed? So we can derive the mathematical relationship of orbital speed with the help of this gravitational force formula. Let's suppose we have a planet. Let's suppose the planet is Earth, and a satellite is moving around this planet. So what is the force exerted by this satellite, by this planet to this satellite? So this relation is known as this Fg, whereas Fg stands for the gravitational force. Capital G is the gravitational constant of the planet. If we are taking Earth, so we have to use the value of Earth. Okay, the gravitational constant of Earth. Whereas this capital M is the mass of that planet. If we are taking Earth, so this capital M is definitely the mass of the planet, mass of the Earth. And this small m represents the mass of the satellite which is revolving around that planet. Okay? And this R basically
Mm.
represents the radius, the total distance between planet and that satellite which is revolving. So these factors now you know.
Yeah.
So can you tell me this capital G represents what?
Oh, G, gravity,
Capital G.
gravity,
Yes, gravitational constant. And what about this capital M?
mass,
Yes, but whose mass? Planet or satellite?
planet's mass, the planets.
Yes, the planet. And the small m?
Um, I can't remember.
The small m is basically the mass of the satellite, okay? Capital M is the mass of the planet, and small m is the mass of the satellite. Is that okay?
Yeah.
Okay. And can you tell me this R? What does R represent?
Uh, radius
Yes,
between.
radius. Or you can say the distance between planet and satellite, right?
Yeah.
Okay. So this force is called as the gravitational force. F represents by force, and this uh, small g, which is in subscript, represents the gravitational force. Now, this is one formula. And the other thing we know that your satellite is moving In which motion? Circular motion, right?
Mm-hmm.
So if that moving in circular motion, so everything that is moving in circle is known as centripetal force, right?
Yeah.
So you have to use the formula for centripetal force. We already did the topic centripetal force in previous lectures. So can you tell me what is the formula for centripetal force?
Uh, F C equals mv
Yes.
squared over r.
Yes, you're right. So FC means F is the force, and this small c basically represents the centripetal force, right? So centripetal force is equals to mv squared divided by r, whereas m is the mass of the satellite, this v is the speed of the satellite, and this r is basically the radius of the satellite. So this is your centripetal force and this is your gravitational force. Now what you have to do, we are doing the derivation for orbital speed, means we have to find the value of v, only v, okay? So for that, what we have to do, we have to compare our both equations. This equation and this equation. This equation is also equals to F force and this equation is also equals to force. So what we have to do, we have to equate both forces. So what we have to do, this becomes equals to this, right?
Yeah.
So any cancellation here?
The F
Yes,
or the M.
yes, small m cancels. So this cancels with this, you will left with this. Okay, now we are resolving our equation for v, but here you can see the r is extra. So what we have to do with this r? Any more cancellation or what we have to do?
Um, could you times it to the other side?
Yes, we have to move this r to the other side. And this is in denominator. But once they move to the other side, they go into the numerator. And you see here is already r square. But when this r comes into the new numerator, so this r cancels with one of this r. Am I right?
Yeah.
So you are only left with single r. Okay?
Mm-hmm.
So this is your equation. But here you can see here v square. We need the only expression for v. What we have to do?
Uh,
But if we have to
Square root
do,
it.
yes, if we have to remove the square, we have to take square root on both sides. So you have to take square root here and you have to take square root here also. Okay. So
Yeah.
what happens? Square cancels. This square cancels with this square root. So you will only left with v, and here you can see under root gm divided by v. So here is your
Yeah.
expression for gravitational speed. V equals to under the root gm divided by r. This is very important formula. You have to remember this formula, right? Okay.
Yeah.
Keep remember this formula. We have to use this formula in numerical. This formula is for speed. Speed.
Yeah.
Satellite speed or planet speed?
Satellite speed.
Yes, this is the satellite speed. Okay, so from this equation, you can easily calculate what is the speed of the satellite that is revolving some a massive body, some other massive body, right? Okay.
Yeah.
Now move on towards types of orbits. There are two types of satellites, which we already discussed. One is the natural satellite and the other is the artificial satellite. But now we are dealing with orbits. Orbit means revolving in a circle. And there are two types of orbits also. One is called as geostationary orbit and the other is called as the lower Earth orbit and it is also called as LEO. Okay. What is geostationary orbit means? Geostationary orbit is where the altitude is 36,000 kilometers. Okay.
Mm-hmm.
This is the altitude of the geostationary orbit. If some satellite is moving at this altitude, so you can say the satellite is orbiting in geostationary orbits. Okay,
Yeah.
perfect. And if the period is 24 hours, what does this period mean? This period means time. How much time your satellite takes to complete one revolution? Okay, one circle. So the time is 24 hours. Okay, it means uh, it took 24 hours to complete one complete cycle for a satellite. Is that okay?
Yeah.
Hmm. And basically, geostationary orbits are used for TV communications, weather communications, and our communication systems, our internet, everything else. Okay. So keep remember these factors. Altitude must be 36,000 kilometer above the Earth. If we are taking Earth as an and the period must be 24 hours. So this is known as the geostationary orbit. Now move on towards the lower Earth orbit. If your altitude is just 160 kilometers, let's suppose if your satellite is moving with an altitude of 160 kilometer above the Earth, okay, or you can approx 160 to 2000 kilometer. If this altitude, so you can say your satellite is moving in lower Earth orbit, right?
Yeah.
Hmm. And in this scenario, the period is 90 minutes. What does this means? It means if a satellite is moving in lower Earth orbit, it took 90 minutes to complete one revolution, or you can say one circle. Okay.
Yeah.
And these lower Earth orbit satellites are basically used for Earth imaging. Like you can see our Google Map. Our Google Map is working on lower Earth orbit. And ISS, International Space Station,
Mhm.
this is also revolving in lower Earth orbit, and also some space satellites. All right.
Yeah.
Okay. Any question?
Nah.
Okay. Now move on towards worked examples. Here is our example number one. A satellite completes one orbit in 90 minutes. One orbit in 90 minutes. What is the period in seconds? You just have to convert minutes into seconds. Can you convert minute into seconds? You can. Can you tell me?
Hmm.
Hmm.
5,400 seconds.
Yes, how?
Times it by 60.
Yes, 90
So
multiplied
it's
by 60 because 1 minute contains 60 seconds. And you have to find for
yeah.
90 minutes what you have to do. Just multiply 90 by 60, you will get your answer, which is in seconds. The next problem is a satellite. Okay, so can you tell me which orbit is that? Either geostationary or lower Earth orbit.
Lower Earth,
How you know that?
because it was 90 minutes.
Yes, 90 minutes. You know that the only satellite which covers one revolution in 90 minutes is the lower Earth orbit. Good. Now, second example, a satellite is 300 kilometer above the Earth. Radius of Earth is given, which is 6,400 kilometers. Find its orbital speed. You have to find the orbital speed. What we derived here. Okay, you have to find this v, and the radius of the Earth is given, which is 6,400 kilometers. So here, but this is in kilometers. And you know what is the SI unit of radius? Can you tell me what is the unit of for radius?
Uh,
Meters.
Unit.
Yes,
Oh,
meters.
so,
So you have to convert kilometers into meters. Okay.
okay.
Hmm.
Yeah.
You know what is the value of kilo?
A
What is the value
thousand.
of kilo?
1000.
Yes, 1000. So 6400 multiplies by 1000, you will get your answer, which is 6.7 into 10 raised to power 6, approx. Okay.
Hmm.
But here you can see what we do here. A satellite is 300 kilometer above the Earth. If satellite is 300 kilometer above, so what is the total distance between that satellite and the center of the Earth? First, you have to take the radius of the Earth, which is this. And again, your satellite is again more away from the Earth, which is 300 more kilometers. So what you have to do, you have to need the total radius. For do so, you have to sum up both distance, which is 6400 plus 300. You will get your total distance, which is 67,000 kilometers. Do you get this point?
Yeah.
Okay, this is the radius of the Earth, and the satellite is again 300 kilometer above the Earth. So this total distance between these two objects is 6,700 kilometers. And now you have to convert kilometer into meters. You know what is the value of kilo? It is 10 raised to power 3, or you can say 1000. 1000 multiplied by 67,000, you will get your answer, which is 6.7 multiplied 10 to the power 6 meters.
Hmm.
Okay, so here R is given. We know what is the formula. Can you tell me what is the formula for orbital speed?
V,
Yes, V equals to
V equals to G gravity mass over gravity mass, like planet mass, and satellite mass. Or
Hmm. Here
is it?
you can see here what we derived here is we will left with only capital M. The small m cancels. Okay, this is our
Hmm.
gravitational force formula. But what is our orbital speed formula? Here is our orbital speed formula. We don't take this is force, but we take this formula, which is V equals to capital G, which is gravitational constants, multiplies by M, capital M. And you know, capital M is basically the mass of the Earth divided by R. R is the
Hmm.
total distance between satellite and the object. So we have to take this formula.
Hmm.
Okay. So you can see we
Yeah.
are taking this formula. So R is given this. Okay. G and M is not given. So how we get the value of capital G and capital M? Basically, the values for capital G and capital M are constants. They are universal constants. You have to remember these values. Okay, they would never be mentioned in the problem. You must have to remember these universal constants. So the value for G is 6.67 multiplied by 10 raised to power minus 11. And the value for capital M, which is the mass of the Earth, it is 5.97 multiplied 10 raised to power 24. Sometimes we take just 6. When we round off, we will get 6. So you can easily remember 6 multiplied 10 raised to power 24. Is that okay?
Yeah.
So keep remember these values. The mass of Earth is this, and the gravitational constant is this.
Yeah.
Gravitational constant and the value of gravity, these both are different things. You know what is the gravity of Earth? Can you tell me?
9.81.
Yes, 9.8. Is this the value of capital G or small g?
Uh, small g.
Yes. So 9.8 is basically the value for small g. And the value for capital G is here
Uh,
6.67
pod.
multiplied 10 raised to power minus 11, right?
Yeah.
So now you just have to put these expressions in the formula. So here you can see the value of G 6.67 multiplied 10 raised to minus 11 multiplied mass of Earth, which is 6 multiplied 10 raised power 24 divided by the value for R, which we find here 6.7 multiplied 10 raised power 6. Once you calculate by using a calculator, you will get your answer, which is approximately equals to 7.73 kilometers per second, because you know what is the unit for velocity or speed? Meters per second. Okay, or kilometers per second. Is that okay?
Yeah.
Okay. Now move on towards our last problem. A satellite of mass 1000 kg orbits at radius of 7000 km. Calculate the gravitational force. Now you have to calculate the gravitational force. Two things are given. The one is the mass is given and the other is the radius is given. So definitely a satellite.
Mhm.
So definitely the satellite is revolving around something. So you must, if it is revolving, so it means you have to use the formula for centripetal force. Okay, so okay, here what
Yeah.
you have to do, you have to find the gravitational force. So can you tell me gravitational force is represented by Fc or Fg?
F uh FG.
Yes, gravitational force Fg. This is your gravitational force, and this is the formula for centripetal force. Okay, if they ask you to find centripetal force, you have to use the formula for centripetal force. But here it's mentioned you have to find the gravitational force. So you have to use this formula which we take initially, Gmm divided by r square, whereas G is the gravitational constant, and you know what is the value for this. This is not mentioned in the problem. You have to remember this value, which is 9.66.67 multiplied 10 raised to power minus 11. And again, the value for capital M is not given. You have to remember the value, which is 5.97 multiplied 10 raised to power 24. It is the mass of the Earth. Whereas small m is always given. And small m is basically the mass of the satellite. And here you can see the mass of the satellite is given. What is that? 1000.
1000 kg.
Yes. And the distance, the radius is also given, which is 7000 kilometers. Again, this is in kilometers, so you have to convert this into meters first. So you just have to put the value of kilo, which is 1000. So 1000 multiplied by 7000, you will get 7 multiplied 10 raised to power 6. Am I right?
Yeah.
Whole square. So now you just have to calculate, substitute by using a calculator, you will get your answer, which is approximately equals to 8.13 multiplies by 10 raised to power 3. And what is the unit for force?
Newtons.
Yes, Newton. So any question related to these problems?
No.
Okay. Here is quick quiz for you. So can you tell me what is a natural satellite?
Uh, uh, something in space like the moon that orbits a planet.
Yes. This is man-made or not?
No,
Okay.
it's
So
not that.
example, give me one example of natural satellite.
The moon.
Yes. The next question is, what provides the centripetal force for a satellite?
Uh, uh, Gravitational force from the planet.
Yes, the gravitational force is the force which allows your satellite to move in a circle. So that's why you can say the centripetal force is provided by the gravitational force by the planet. Okay, right. Name one use of geostationary satellite. Can you tell me one of the application of geostationary satellite?
Like a TV satellite.
Yes, TVs and
Weather.
yes,
Weather
weather
channel.
forecasting, etc. Okay. The next is If radius increases, whose radius? I'm concerning, I am the distance between the planet and the satellite. So if the radius increases, does satellite speed increases or decreases?
Uh, Decreases.
Yes, decreases. How?
Um, because it's getting further away.
Yes, it's further away. You are right. So you can also check this mathematically. This relation what we derived, right? So here you can
Hmm.
see this is the speed or velocity, and here is the radius. Can you tell me what is the relationship between this v and r? Either it's a direct relation or inverse relation.
Uh, Inverse.
Yes, inverse, because you see here your velocity speed is in numerator, and here you can
Hmm.
see your radius in denominator. So there is an inverse relation. And you know what is the properties of inverse relation? If you increase one thing, the other thing is decreased. If you decrease this thing, the other thing is increased, right? So
Yeah.
same question is here. So if radius increases, so speed
Mm-hmm.
decreases, right?
Yeah.
Because there is an inverse relationship between the radius and the speed, according to the formula what we derived in today's lecture.
Yeah.
Okay, so the last question is, what is the typical altitude of a lower Earth orbit?
Um, 160 to 2,000 kilometers.
Yes, so if some satellite is revolving in this altitude, we can say then the satellite is revolving in lower Earth orbit. And can you also tell me the altitude for geostationary orbit as well?
Um, like
Do you remember?
mm, 36,000 kilometers.
Yes, here it is, 36,000 kilometers. Okay,
Mm.
so here are some assessment questions for you. You can do practice at your home. Okay,
Yeah.
okay, and this thing you already know, the International Space Station, the ISS, it takes 90 minutes to revolve one revolution around the Earth. So the orbital speed of ISS is 90 minutes. Okay, keep remember this. And
Yeah.
without Earth's gravity, satellite would fly off in a straight line into the space. Definitely, if there is no gravity, so your object is not allowed to move in a circle. There is no centripetal force, and if there is no centripetal force, so definitely your satellite would fly off in a straight line and into the space. So this is all about our today's lecture. Do you have any question? You can ask.
Nah.
Okay, so that's all for today's lecture. Take care and
No.
Allah Hafiz. Thank you.
Office. You too. Right. Bye. Bye.
Thank you, Allah.